we are going to learn theorem 6.10.1 in this video. You can see this theorem in the 5th unit of advanced algebra paper. Okay, so here you can see this theorem. It's a very important theorem, university question also. So let's learn this theorem in this video. Here you can see the statement, the linear transformation T on V, that is they are given you a linear transformation, that is T. This linear transformation is present in where? V. Okay, is this linear transformation T is unitary. When it is unitary, if and only if it takes an orthonormal basis of V into an orthonormal. It is an if and only if statement, no? So what you are doing is you will have two parts. As you all know, it is having two parts. So here what you are doing is, first you are assume T is unitary. By assuming T is unitary, you will prove this T takes an orthonormal basis of V into an orthonormal. Okay, so let us see the proof of this theorem. Assume T is unitary. By the definition of unitary, you can write this. UT, VT, inner product, okay? You have to read like this. Inner product of UT, VT is equal to UV. For all, this U and V belongs to the vector space capital V. Is that okay? You are writing this by the definition of unitary. Now, to prove, what you have to prove by assuming T is unitary, this V1T, V2T, etc. Vn is an orthonormal basis of V. That is what we are going to prove. That is to prove this is an orthonormal basis of V, it is enough to prove these two conditions. Okay. These two conditions are come from the definition of orthonormal basis. Okay, that you can see in the first unit. So here, by the definition of orthonormal basis, it is enough to prove these two conditions to say V1T, V2T, etc. Vnt is an orthonormal basis of V. So here first condition is Vit, Vit, same elements inside the inner product space. So inner product space Vit, Vit is 1. If it is different means value will be 0. That is the value of, if the I and j value are different, then this, okay, this value inner product of Vit, Vjt equal to 0. Okay, Vit, Vit is equal to 1, Vit, Vjt equal to 0 for I not equal to j. Okay, we are going to prove these two conditions. So to prove these two conditions, before that you have to do something, that here first what you are writing is, you are taking an orthonormal basis of V. Okay, here you have to prove this is an orthonormal basis of V, but what you are doing is, you are taking, let V1, V2, etc. Vn, wait a minute. Let V1, V2, etc. Vn be an orthonormal basis of V. You are taking like that. With the help of these two, you will prove what we have to prove. Okay. So here you are taking these be the orthonormal basis of V. Then these two conditions. By the definition of orthonormal basis, you are writing these two conditions. Vit, Vit is equal to 1 and Vi, oh my god, what I am saying, Vi, because here you are taken V1, V2, etc. Vn is an orthonormal basis of V, no? So by the definition of orthonormal basis, you are writing like this. So here you are going to prove V1T. Here you are having T with each terms, each elements. So that is why here when you write these two, you are having Vit equal to 1. Vit, Vjt equal to 0, like that. So now you are taken, this is the orthonormal basis of V. So by the definition of orthonormal basis of V, you will get these two conditions. Now using these two conditions, you will prove what they are asking us to prove in the statement of the theorem. Consider Vit, that is, we are going to prove these two now. So first let us prove this. To prove this, you are considering the left hand side and you will bring the right hand side. Okay, by consider the left hand side. So this can be written like this, Vi, Vi. Okay, how you can write like this? You are writing like this. You assumed that T is unitary. No, unitary means you have this condition. No, by the definition of unitary. So you are applying this condition there so that you will get VIT comma VIT is equal to VI comma VI. You know that VI comma VI is 1. So just put that value. So you proved the first condition. And here you are going to prove the second condition. So to prove the second condition, first you have to consider the left hand side of second condition. So this is our left hand side of second condition is equal to, this can be written like this. How? By the definition of unitary. By our assumption, you can better say. So you know that Vi comma Vj equal to 0. So you got 0. So you proved two conditions to say this is an orthonormal basis of V. No? So you can say therefore VIT, this is an orthonormal basis of V. Okay. So you proved the first part of this theorem. Now let us pass on to the converse part. The converse part, you are assuming this. Okay. In the converse part, what you are going to do? What you have assumed in the first part, that you will prove here. Okay. The thing that you proved in the first part, you will assume that in this part. Is that clear? Now you are assuming this. And you will prove T is unitary. That is to prove, by the definition of unitary, that is to prove, you are going to prove this. Ut comma Wt is equal to U comma W for all U comma W belongs to the vector space capital V. Okay. Now, you know that let U comma W belongs to capital V. U can be written like this. The reason is because you are taking U and V from the vector space. No. So that is why the elements, these are the two elements present in the vector space. So these elements are in this format. Okay, the elements present in this capital V will be in this format, linear combination format. Okay, linear transformation. So here U is equal to, the element U will be in this format, alpha 1 V1 plus alpha 2 V2 plus etc. plus alpha n Vn. So this can be written like this. Here you are having plus, no? So that is why summation from I equal to 1 to n alpha I Vi. Okay. So U can be written like this. Similarly W, the element W will be like this, and this can be written like this. So I hope you understood till this. Now U comma inner product, consider U comma W. You are going to find this. Okay, that is, you are considering the right hand side. From this you will, at the end you will bring this. Okay, that is what you have to prove. No, you will bring that. So let's see how. U comma W is equal to, you know that the substitute the value of U here and substitute the value of W. Okay, now this can be written like this. That is, this value comma this value, put the plus, and this value comma this value plus etc. plus this value comma this value. That is what you are writing. No, this value comma this value plus, then this value comma this value plus, then this value etc. plus this value comma this value. Okay. So you finished till this, then plus, then alpha 2 V2 comma this plus alpha 2 V2 comma this plus alpha 2 V2 comma this, then plus etc. plus, then alpha n Vn comma this plus, then alpha n Vn comma this plus alpha n Vn, in between you have to put etc. plus alpha n Vn comma beta n Vn. Like that you have to expand this value. After that, what you are doing is, you are bringing from this, look at this, from this you are bringing alpha 1 and beta 1 outside that bracket, outside the inner product space. So when you bring alpha 1, that alpha 1 will come alpha 1, but beta 1, you are taking beta 1 from the second term, right? that present in the inner product space. It is in the second term. So when you bring an element outside from this, that will come like this, beta 1 conjugate. The conjugate will come like that. When you take the element present in the second term of the inner product space, that will come like this. Alpha 1 will come like alpha 1 when you take alpha 1 outside, but beta 1 will be coming like this, beta 1 conjugate of, then write the remaining v1 comma v1, plus similarly do for each inner product spaces. So you will get this, okay, and then you get this. Okay, now what you are doing is beta 1 alpha 1 beta 1 v1 v1, that is you know that if there is a same inner product space, if there is I values are same, means you will get 1. The I not equal to j means you will get 0, no? So when the different values, this all becomes 0. Okay, these all become 0. Everything will be 0. This is also 0. This is also 0. Only these terms will be present. V11, V22, V33, V44, etc. Vnn terms, that will be that only present here. So that is why you are writing. All the other become 0. How they become 0? Because that from the in the assumption you have assumed like that. Right, v1, v2, etc. vn be the orthonormal basis of v, and you are having these conditions. So using these conditions you have done that. Now what you are doing is the v1 value is 1, no? This is 1, this is 1. So that you will get this alpha 1 beta 1 bar plus alpha 2 beta 2 bar plus etc. alpha n beta n bar. Now this can be written like this, summation I is equal to 1 to n alpha I beta I bar. Right, so you found the value of inner product u comma w. Now what you are doing is, now you are considering the right hand side. The right hand side, when finding right hand side, now you are finding the left hand side. When finding left hand side also, you have to get the same value. Then this condition will be proved, no? So that is what you are doing. Now consider the left hand side. ut comma wt is equal to, ut can be written like this, wt can be written like this. You know the value of u, put this and write t with that, comma, write the value of w and put t like that. From these two, you are taking summation I is equal to 1 to n alpha I and beta I bar outside. Okay, so that you will get, here you don't put beta I bar, sorry. So the when the element present in the second term of within this inner product space, that when it comes to outside, it will come with a conjugate, right? So that is what happening. Already I explained you the same thing happening. Summation I is equal to 1 to n, put this alpha I, and when this come outside this bracket, it come like this, beta I conjugate. Write the remaining things. Then I same, no? Same means the value of this is equal to 1. So that is why you are getting this term in the next. Then this is equal to this, right? Because just before you have done like that, this value is equal to this, no? So you are substituting this. So you found, finally you proved the condition to say T is unitary.